So today I'm finishing up chapter 10, and during next week we will work on chapter 11 as well. My plan for the final is to include chapters 7, 8, 9, 10, and 11. I'll write this down for you to see. And I'm not gonna continue with chapter 12, so the material is less. And regarding
Professor? I can't hear you very well. I'm not sure if it's only me.
give me a second. Yeah, I should fix my mic. Give me a second. Yeah, so we defined our angular kinematic quantities to replace the translational ones. Yeah. We defined angular velocity, and we wrote some kinematic equations, angular displacement, and angular acceleration. And these were their equivalents. So we always just substitute x by theta, v by omega, and a by alpha, which is the angular acceleration. Now, we talked also how we can link these two. We use the equations of kinematics for a constant angular acceleration. They look the same as the ones we use for translational or linear motion. And later we also linked the angular quantities to the linear quantities. Namely, we said theta is s over r. And then by deriving every time with respect to time, we deduced that omega is also going to be linked to the speed. So we can write omega to be v over r, and alpha is a over r. Now, we mentioned in particular that the v that we are studying here is none other but the tangential velocity. However, in circular motion, the tangential velocity is the total velocity itself. So it's okay. We didn't really have to label it as tangential. But just to say that it has a tangential direction, I will always put a subscript t with the velocity. Now, we notice also that the acceleration that we will get from here is going to be a tangential acceleration. You all agree? This is tangential because I obtained it by deriving the tangential velocity. So this is a tangential acceleration. And from it, I found the angular acceleration. However, I know in this circular motion, the acceleration is not just tangential, it's also going to have a centripetal component. We talked about this somewhere here. Yeah, so we said our acceleration, which we found, and linked to the angular acceleration, is actually the tangential component of our acceleration. The real or total acceleration should also have a centripetal component, right? So if you look at our acceleration, it must have a centripetal component so that the velocity keeps tilting along the circle. If the velocity, let's say, the velocity is always tangential, right? So if the velocity here, I draw it, it will look like that. And if the acceleration was just the tangential acceleration, then the velocity will just keep increasing upward because the tangential acceleration just has the same direction as the velocity, so it will just add up to our velocity. However, our velocity was not just increasing, it was increasing for sure, but it wasn't just increasing, it was also getting tilted such that it looks like this. So let's say I'm now at this point. My velocity would basically be a tangent again, which is like this. If I go to this point, longer velocity, but also tilted, the tilting must be coming from the acceleration vector as well, which means that the acceleration vector is not just tangential, it also has another component that is not tangent to the path, and thus we define the centripetal component of our acceleration, which is none other but v squared over r, because we studied this from uniform circular motion. We have a centripetal acceleration, which is equal to the speed squared over the radius. And the speed is always tangential. So when I write v squared, this is the total speed or the tangential speed that we have studied before. So this is vt squared over r. And now we have two components for the acceleration, a tangential one and a centripetal one. Now the centripetal acceleration is just v squared over r. Now v is just a tangential velocity always, so I'll write it as vt. Whereas the tangential component, we found it from the angular acceleration. I remind you, we said the centripetal acceleration can be found from the angular acceleration. It's alpha times r. And of course, we can find alpha from omega, which is the angular speed, and so on and so forth. Okay, and then we defined also the angular form for the kinetic energy, or this is the kinetic energy stored in rotation. If I have a rotating object, I will have some kinetic energy that is stored in this object, and I can find this kinetic energy. Now, of course, the original formula works, which is half mv squared, but as usual, v is varying across the different points, which is not convenient, right? I will have points closer to the axis of rotation. They will have less or more linear speed. Points that are closer to the axis, so such as point 1 here, which is at a distance r1, it's closer to the axis of rotation than point 3 here and point 2 here. Points that are closer will have less or more linear speed. Less. Why? They have less distance to cover as they rotate. Their arc length is less than the points that are further from the axis of rotation. So in terms of the linear speed, the points closer to the axis must have less linear speed, right? But in terms of the angular quantities, the angle covered by each point here is how much it's the same, right? This is a blade for the helicopter, probably in the previous problem. And the blade here has different points. Each point is covering the same angle, however. Like the points start here, let's say they rotate a little bit all the way here. They all cover the same angle theta, and thus they will all have the same angular speed omega and the same angular acceleration. So in terms of angular quantities, things are more constant and easier to study than linear quantities. So instead of using k equals half mv squared, I will try to define a new expression for k in terms of the angular quantities, which are more convenient to study. In fact, if you use just the kinetic energy equation for the linear quantities, you will have to put the summation of half all of the masses times their speeds squared, because different points will have different speeds. So I'll have to take the mass of every point and multiply it by the speed at that point, right? Whereas if you try to transform this into angular quantities, namely, I'm going to substitute v by omega r, and then I'm going to rearrange my equation. It will look like half sigma m ri squared times omega squared. Now, this quantity here, sigma mi ri squared, is just related to the dimensions and the mass of my object. I'm going to define it as the rotational inertia. And now my kinetic energy looks like this. Half I omega squared. It's a quantity that doesn't have to sum across different points of the object, as in this form. In the form which contains the linear quantities, you have to sum across different points. Whereas in this form, where you contain angular quantities, you substitute the linear ones by angular ones, then the equation doesn't have a summation. You don't have to look at different points across your the blades, let's say in this example, and thus it is simpler and easier to study. Makes sense?
Professor?
We can use either form, by the way, of course. Yes.
I just wanted to ask you, نحن we're only like we
Now, regarding our new quantity, the rotational inertia of an object, which we defined in the previous slide, basically that quantity was the mass of the object times r squared, where r is the distance to the axis of rotation. And of course, we are adding across different points of our object because these will have different distances. Now, one thing you notice is most objects have a continuous distribution of mass. Namely, I have, let's say, our sphere. Different points of the sphere will have different distances to the axis of rotation. So if I'm considering this axis of rotation and the points across the sphere are distributed as such, then maybe point 1 here is at this distance r1, point 2 is at a larger distance, but I have a continuous distribution of the mass. It's not like particular particles which I can add up. So rather than adding up the masses of each particle, which is not possible because I have infinitesimal masses and infinite points. So what I have to do is I will upgrade the formula of the rotational inertia to an integral rather than writing I to be equal to the sum of mi over I squared. I'm going to integrate over the infinitesimal masses that I have because we have this continuous distribution of mass everywhere. So I will have to integrate over an infinitesimal mass all the way from 0, let's say, to the final radius of this sphere, which is the object I'm studying here. Now, like I told you, I don't want you for now to work on the integrals. I don't want you to sit and solve for the rotational inertia, but I just want you to understand how the formulas come from. They come from the integration of the different positions across different infinitesimal masses. So I want you to just look at the table, which contains the final answers for the integrations for different objects and different axes. Namely, the same object, but with different axes, will have different rotational inertia. And this is only because the points will have different distances to the axis when I change the axis. So the same rod, if the axis passing through its own axis, the points will have these distances to the axis, right? Whereas this rod, the axis now is perpendicular to its own axis. You can see how the points have new distances to think of. And thus, we have something, we have a new integration to work on, and the rotational inertia will not look the same, even if the two rods have the same mass. So what you are rotating around is just as important as the shape of the object itself. So I will define the rotational inertia for the rod when the axis of rotation is the axis of the rod itself, as in figure C. The rotational inertia is half mr squared. I have also defined the rotational inertia for a hoop, and this hoop is rotating around its own axis again, the axis that is passing through its center, and the rotational inertia is mr squared. Here I have a ring or an angular cylinder, so this is empty in the middle, but it has some non-zero thickness, and then I have to account for both radii, and the rotational inertia is half mr1 squared plus r2 squared. I have here a rod with the axis perpendicular to its own axis. The black line is the axis of the rod, which is basically the line along its own length, and the axis is perpendicular to it. So basically the rod is rotating like that, right? Here the rod is rotating as such around itself. So in figure E, the rod that is passing and rotating around this new axis will have its rotational inertia to be 1 over 12 ml squared. So you have to be careful in the problem what shape you have and around which axis this object is rotating. Yes. This table is given to you in the exam, yes, in the formula sheet. As it is, I will print it in the exam as well. Okay, so you just look at the table and check which object you have, which case you have. All right. Yeah. Sorry. In figure D. Let's see. So in figure D, I have a solid cylinder about its central diameter. And this one, I have a thin rod. Hmm? Oh, yeah, there's a plus sign for sure, yes. So basically, the difference between D and E is that here it's just like a thicker rod. The radius is significant. Here I'm considering the radius to be not significant. All right? Yeah. In figure G, by the way, and in figure F, in F, I have a solid sphere. So just be careful about the difference. In figure G, I have a thin spherical shell. When I say the word shell, how is that different from the solid sphere? It's hollow in the middle. It's empty in the middle. Yeah. This is empty inside, which makes the study easier. The particles are just across the surface outside. I don't have to integrate along the whole radius. And you are given, as usual, the final answer, I is 2 over 3 mr squared. A solid sphere moving about its own diameter, 2 over 5 mr squared. Let's say I have a solid sphere and it's rotating about this axis here. And it is at a distance d from this axis. How do I find the rotational inertia of this sphere? Let's say this is a small sphere, so I would say, let's say d is way bigger than r. So I can assume this sphere is a particle. Do you all agree? All points have the same distance d to the axis. What would I write for the rotational inertia? So sometimes I would ask you to derive the rotational inertia, but I will give you simple cases. I'll give you particles such that you don't have to integrate. If you don't have to integrate, what was our formula? Yeah, it was mr squared, none other but mr squared. So our initial formula for the rotational inertia was r squared, where r is the radius. Is r the radius? It's the distance from the particle to the axis of rotation. And how much is that here? It is d, yes. So here I will have m d squared, and that's it. I used the basic formula for a particle. Now, if I had multiple particles, let's say I had a point here and a point here, and they are connected together. So it's like a stick and two spheres at the end. You can say this is, I don't know, a nitrogen molecule, up to you, and then this whole thing is rotating. How do I find the rotational inertia here? Hmm? Yeah, they are both at an equal distance d, and the rod is essentially always vertical throughout the rotation. And let's say I told you the rod is massless. Okay, let's say the rod is massless. I'm gonna put this in a separate slide so we can work on it in detail. Okay, so what I have is, I want you to find the rotational inertia of the system of two spheres connected by a massless rod and the system rotates around the below axis. So we have a figure, two spheres, massless rod, and this is the axis of rotation. Usually the axis is labeled by this arrow. It doesn't mean the rotation is counterclockwise. This is just to tell you that this is the axis of rotation. All right, just as the x and y axes, I would put an arrow here and here to tell you that these are axes with a given direction. So this is just to say that this is an axis of rotation. So the whole system is rotating around this axis. Maybe it is rotating in this direction. And the distance is let's say 2 meters, and the mass of each rod is 2 grams of each sphere. So I want to find the rotational inertia. When you're asked to derive the rotational inertia, you will always have to use the same formula because we didn't really take any other formula. So I'll use sum of mi ri squared, right? Previously, I just put mr squared without summing because I had a single sphere. I didn't need to sum really, and the basic formula is mr squared. Here I have two spheres. The rod is massless, so I'm gonna put sum of m r squared for each of the particles or parts of my system. My system contains two spheres, right? So this will be m of sphere 1, distance of sphere 1, plus m2, r2 squared. I can put the mass of the rod, r of the rod squared, but it is massless, so I'll cancel this out. And now the two spheres are identical, and both are at 2 meters from the axis of rotation, right? So this is really easy. M1 equals M2 equals 2 grams, and R1 equals R2 equals 2 meters. So I'll end up with 2 times 10 power minus 3 times 2 meters squared times 2, because I'm adding this twice, and I will get the final answer. 8 times 10 power minus 3. What is the unit, by the way? This is M times R squared, so it is kilogram meters squared. Yes. Now, let's say the rod is not really massless. Same problem. But rod is thin rod of mass equal to, I don't know, 10 grams. What do we do? So now my system looks like this. This is now significant. It's not massless. It's a particle by itself. I still have the same axis and the same distance, 2 meters. I'm gonna essentially start with sigma mi ri squared, and this will be m1 r1 squared plus m2 r2 squared. However, for the rod, I will not just write that as mr squared. I have to put the rotational inertia of the rod itself. What is the rotational inertia of a rod? I will move to the table of rotational inertias. Now I have 3 cases for rods. Well, for this one is for a thick cylinder. For rods, I have these 2 cases. Now, our rod satisfies the difference between the 2 cases is none other but the axis, right? These rods in figure C and in figure E, they are the same, right? Same rod, same mass, but one is rotating about its own axis. The other is rotating about an axis that is perpendicular to its own axis. Which one do we have? C, we have something similar to C. Actually, the rod in our problem is not rotating about its own axis, but it's rotating about an axis parallel, exactly, parallel to it. So what am I gonna do? Is it gonna be the same rotational inertia? This is half mr squared, right? So I'm gonna write it down just to keep it in front of me. Where was our question? It is for a rod rotating about its own axis. So if our rod was like this and the axis of rotation was here, then I equals half mr squared, where r is the cylinder's own radius, right? So in our case, we have the rod rotating about this axis, but this axis is parallel to that axis, so I can use the parallel axis theorem. Here, our axis is parallel to the axis of the rod, so use the parallel axis theorem. What does the parallel axis theorem tell us? It tells us that the rotational inertia around a certain axis is equal to the rotational inertia around the axis passing through the center of mass plus mh squared, where h is the distance between these two. I'll write this down in our question. I is I for the axis of rotation passing through the center of mass plus mh squared. Let's say our rod has a radius 1 millimeter. So the rotational inertia around the center of mass is going to be the one for a rod rotating about its own axis, which is half mr squared, plus m times h is the distance between the two axes, which is basically 2 meters plus 1 millimeter. So this is 2.001. It's approximately 2, right? So this is none other but r, which we had in the previous part. I'll just leave it as it is before I substitute numerical values. So the mass is 10 grams. I'll write this as 10 minus 2, and I'll multiply that by the radius squared, which is 10 power minus 3 squared, plus the distance squared, which is 2 squared. And I can calculate the rotational inertia for the rod and then add that up here. You will notice that, in fact, which factor dominates? Is do you notice how I of the center of mass compares to the term next to it? Which factor is going to be bigger? Look at the numerical values, this versus this. mh squared is going to be way bigger than half mr squared, which is the rotational inertia of the rod rotating around itself. What does this tell me about the rod? It acts almost like, so its dominant is the second factor, which is just mr squared. And mr squared is the rotational inertia of what?
Particle.
Of a single particle. Yeah. So the rod is basically acting like a single particle. Why? It's simply because its radius is so small, it's acting almost like a particle. Its own rotational inertia, which is half mr squared, is just so insignificant. What matters is just its mass and its distance to the axis of rotation. The rod is acting almost like a particle in this particular case because I selected this very tiny radius. Any questions?
Professor?
Yeah.
Can you please go over the formula we used?
The formula we use?
Yeah, because you mentioned you went back to the formula sheet and you were choosing which formula. I don't get it.
Yeah. So the thing is, I was asked to find the rotational inertia of the system, a rod and two masses. Do you agree?
Yeah.
Yeah, to find the rotational inertia of this whole object, I look at the shapes I have and I will write down the rotational inertia for each shape and add them up. Because at the end of the day, the rotational inertia is sigma mi r squared. That's the basic formula. Now I have three masses, two spheres and a rod. So I put m1 for the first sphere, r1 squared, plus m2, r2 squared for the second sphere, plus the rotational inertia of the rod itself. Now the rod itself, I will not put only mr squared because it is a rod, so its rotational inertia is not just its mass times r squared. Actually, its rotational inertia is given here in the table of the rotational inertias. Now our rod is basically like this. It is vertical, and it's rotating around an axis that is next to it here, which I don't see in the table, but I do see in figure C, the rod rotating around its own axis. So I can use the parallel axis theorem. I will study the rotational inertia around its own axis, which is half mr squared, and add to it mh squared, where h is the distance between the two axes. Does this make sense to you?
Yeah.
Yeah, so that's what I did. I said the rotational inertia of the rod will be its rotational inertia when it's rotating about its own axis, which passes through center of mass, plus mh squared. Remember, I only use the parallel axis theorem when the rotational inertia is compared to another axis that passes through the center of mass. So I cannot really compare to an axis that doesn't pass through the center of mass. However, if you look at our table, which is given to us, do you notice how all of the axes that we covered in this table pass through the center of mass? So yeah, if I have some rotation around an axis that I don't know, I'll just try to find its equivalent from our table here and just add mh squared, where h is the distance between these two axes. Makes sense?
Yes, thank you so much.
All right. Okay, so I'll move on to what we discussed next, which is the torque. We said the torque tells us if a certain force will generate a rotation or just make translational motion. We gave the formula, F times R times sine theta, where theta is the angle between the force and R is the distance to the axis of rotation. And we defined Newton's law, which is the equivalent in rotation. It will be tau net equals I alpha as compared to F net equals MA. And like I said, so if I have rotation, can I use this if an object is rotating? Can I use F equals MA? Can I use F equals MA if I have rotation? Can I use K equals half mv squared? Can I use K equals half mv squared? I can, but V has to be the tangential. It is tangential. V is always tangential, by the way. Was there any motion where V was not tangent to the path? It's always tangential. But because we have a circle, I like to just name it tangential. So K equals half mv squared is valid, right? Except that it's changing across different points, so it's harder to study. So F equals MA is also valid. I can use it, but you will see it is also harder to study. Namely, in the example I studied here in the figure, remember the wheel with the friction? By the way, you were right about the direction of friction. Yeah, it should be opposing the sense of rotation. So this direction of friction is the correct one. So here, if you look at our figure, we had 4 forces: normal, weight, applied force, friction force. We found the torque for each, and we were able to find tau net. And notice how the torque of the normal and the weight canceled out simply because they are along R, right? The distance to the axis. Now, if I was studying F equals MA, I would have to still worry about the normal and the weight force, okay? And maybe they will not cancel out. So studying the angular quantities is nicer and easier. It will remove many forces, namely all forces that are along the distance to the axis, they will just cancel out. So studying the rotational form always simplifies things, but the general rules will still be valid. Like the first rules we studied for translation are still okay to study. Okay, so I think I'm gonna stop here for today, and the next time I will work on some problem solving. We're finishing up this chapter with just one more remark on the work energy theorem and the formula for the work done. And basically, that's it. Thank you for joining me today, and I'll see you next time.
Professor.